I'd like to talk to you this morning about some graphing basics and things that you should avoid when making graphs. First thing, graphs are big. They should take 2/3 to 3/4 of the available area. So if you are given a grid on a test or a quiz, then you should use almost all of that space to make your graph, like this one. Second, graphs have titles. In this case, they said experimental resistance of a 50 ohm resistor because the slope of this graph is resistance. I prefer the dependent variable versus the independent variable. So for that graph that I just showed you, I would have called it voltage versus current. Either one is good, either is simple and tells what's being graphed. Both axes have to be labeled with the quantity and the units. It's not enough to just say voltage. You have to say voltage, volts. It's not enough to say current. You have to say current in amps. We will be graphing things like position, and the units there would be meters, or time, and the units would be seconds. But they have to have both. Now, once in a while, we'll graph something that doesn't have units, like in the knots lab, and the units of knots was knots, so labeling one axis as knots is fine. The range of your numbers on the axes should be only slightly larger than your data range, so that your plot should not just all be stuck in a corner or just in one small part of your graph. If you make the range that you put on your axes just slightly larger than the range of the data, then you will have a nice big graph and be able to see trends more easily. Your plotted points should take up most of the space of your graph. The intervals on your axis should be equal. You see here, these big lines, they count for 10 each time, 10, 20, 30, 40, 50. So these intervals are the same size. The intervals on the horizontal axis are the same size. Each one of these big grids is 0.1, so 0.2, 0.1, 0.2, 0.3. Students make the most mistakes at the origin, and occasionally I have a student that just flat out puts their data on an axis. And that's not right. You look at your data range, you choose a slightly larger range, you put reference points on your axis with equal intervals, and then you plot the points where they fall. Suppose you don't want the vertical axis to start at 0. Okay, I'm going to hand do a graph really quickly. It's not going to look neat, but let's say all of our data is between 200 and 300 on our vertical axis. So we have a 0 here, and let's say all of our data on the x-axis is, from 0 to 10. So we'd have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, and you please use your grid. I had some students making graphs, and they just randomly put points. On the graph paper, you have a grid for a reason. Okay, so what I saw students do is say, I'm going to let this be 200, and I'm going to let this be 225, and I'm going to let this be 250, and I'm going to let this be 275, and so on. But because I've already made the problem, let's look at the problem. The problem happens right here. If you don't label this, it is assumed to be 0. So what you have is an interval that's 200, and then an interval that's 25, and another interval that's 25 and 25, so you have unequal intervals. What this also makes it look like, it messes up your y-intercept if you draw a graph. If it does happen to go through this point, you assume the y-intercept is 0, and it's not. It's, if each of these little blocks looks like they're 12.5, then this is 200, and so this is 187.5. It's not 0. So if you do want not to start at 0 on your vertical axis, you have to label the origin, okay? Not just start somewhere random. You have to label the origin as something other than 0 if you want it to be something other than 0. The horizontal axis must start at 0. That's how we're going to get our y-intercept, and y-intercepts are important. Please draw a good trend line. By that, I mean it should be drawn with a ruler, not just sketched, not just hand-drawn willy-nilly. And it should clearly or closely approximate the trend of all the data. No point is more important than any other point. So lay a ruler down so that your line goes as close to as many points as possible. It can go through all of them sometimes. In this example, it goes through none of them, or very closely almost goes through this one right here, but it really doesn't go through any of the points. It also does not go through 0. Don't make your graph go through 0. The very worst trend line you can possibly make is to go from your last data point to 0 and draw a line. That's like the only 2 points that matter are 0 and the last one, and 0 is not even a data point. So do not make your graph go through 0. The only reason to draw a graph is to find the relationship between two quantities. The trend line is a representation of that relationship that we can see. It's a graphical visual representation. The equation of the trend line is the mathematical representation of that data set. In order to find the equation, you need slope and intercept. Remember, y equals mx plus b. So to write the equation of your trend line, you have to have the slope of your trend line and you have to have the y-intercept of your trend line. When you find slope, number 1, show the points that you will use to find the slope on the graph. Never, ever, under any circumstances, use data points from your data table. I don't even care if they fall on that line. Stay away from your data points. Once you have your trend line, your data is gone. Your data is not important anymore. The trend line is the representation of your experimental results. Okay, so show me your points. Do you see in blue? There's a point here that is starred, and there's a point here that is starred. Show me the points that you're using. Number 2, show the slope equation. This says delta v over delta I. Typically, you can write delta y over delta x, or you can say y2, not y squared, y2 minus y1 over x2, not x squared. They are subscripts, not superscripts, and that's important. It's not just aesthetics. It's not just I like it this way. It is a language. Math is a language, and when you use exponents, you're saying something very, very different than if you're using subscripts. Okay, so write your slope equation. That's number 2. I want to see the coordinates of your points plugged in. Now, this example plugged them in over here. They found delta v, and here they found delta I. That's fine. So you can see there are the coordinates, the 0.85 minus 0.09, and here are the coordinates, 51.5 here and minus 10. Okay, so show me the points you use and the coordinates of those points plugged into the slope equation. I want an answer, and that answer has to have units on it. The 4th thing that you need to get from your graph is the y-intercept. And you know how to do that. It's where the line crosses the y-axis. You can read that. Finally, you can write the equation. Use variables that represent what you've graphed, not y and x anymore. In this case, the vertical axis was voltage, and the horizontal axis was current. So V, voltage, is equal to 54.6 volts per ampere. That's the slope times the current. I, the symbol for I is current. The symbol for current is I. Plus 4.5 volts. That's what I read the y-intercept to be. Got it? It has units in it. It does not have x and y. It has relevant variables that tell you something about what you graphed. If you now have to make a prediction, use the equation. You have an equation. Plug in values from your equation. So if you had to predict what the voltage is if the current is 2 amperes, you write the equation that you just came up with, plug in the value. In this case, you were given a value for the independent variable, but you might have been given one for the dependent variable and have to solve. So we have plugged a value in, and then we calculate 54.6 times 2 is 109.2, plus 4.5, that's the y-intercept, equals 113.7 volts. And that's our predicted value. You will also often have to find a relative error or a percent error, and those equations, for the time being, you might find them on the board, but they won't be there all year long, so you want to make sure that you have those. Remember, the percent error is an accuracy calculation. How close are you to the right answer? And relative error is a precision. How close are you to the average measure? I hope you found this helpful.